Hello everybody, welcome back. Alright, this is actually pretty easy, this part. Major subatomic particles, a review of elementary school, not even middle school. Protons, neutrons, electrons. And we're going to put everything together here on a chart to organize it for you. But I will say this thing, the other particles. Go ahead and read the little article that's in your textbook about the hadrons, leptons, baryons, etc. And you just have to know the definitions for the test. So I'm not going to sit here and go over those definitions except to kind of highlight a couple of things. We could take the protons, neutrons, and electrons and categorize them into two different types, hadrons and leptons. Hadrons are what they call heavy particles. They can be broken down even further. And leptons are called elementary particles that cannot be broken down even further. But it's an interesting read. And like for instance, the gluons are particles, exchange particles. We're going to talk about that when we get to photons, that actually hold the quarks together to make the protons and neutrons. So I always thought that was an interesting name, gluons. How did they come up with that? Because they stick the other particles together. So I used to have a contest with students of creating their own subatomic particles. Dr. Checker of our school was a theoretical physicist, and one of the things he said was, in order to prove that something exists, you first have to dream that it's possible. And so I came up with these three subatomic particles. Funniest thing is, during the regular school year, students will start taking notes on these. These are not subatomic particles. I made them up. Come on. Pikachuons, please. Goku, come on. Those aren't real particles. But gluon sounds like it's not a real particle either. Alright, so let's go ahead and fill in this chart. Copy it and paste it, because that's what I do. Control C, Control V. Oopsie poopsie. Make it a little larger. Okay. Alright, the protons. The mass of a proton is slightly less. And this is important, this slightly less part. Slightly less than 1 AMU. Whereas a neutron is 1 AMU. Alright, so in fact, the mass of a neutron is actually the mass of a proton plus an electron. And the mass of an electron, which is a lepton, it's a very light particle. Protons and neutrons are heavy particles. The mass of an electron takes 1,800 electrons to have the same mass as a neutron. Alright, so the charge of a proton, well again, the mass here is 0.000000 blah 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 blah. These are relative numbers in AMU. Same thing with the charge. The charge on a proton is 1 times 10 to the minus 19 coulombs. So we're not going to write that. We're going to come up with a relative number, and we just say that the charge is positive 1. That neutrons are neutral and have no electromagnetic charge, and the electrons have the same amount of charge as a proton, but they affect electromagnetic fields differently, so we say that they have a negative 1 charge. Protons and neutrons are found in the nucleus of the atom, and you may have been taught that electrons are found in energy levels or orbitals, but for now, the only thing we're going to say about electrons is that they are not in the nucleus. That's where they are, not in the nucleus, because electrons do weird things. We're going to talk about electrons in chapter 5. So pretty easy chart for you to memorize, and again, a review of elementary school. Alright, radiation. This is actually a little bit of chapter 4, but it's also a little bit of chapter 28. And we're going to talk about nuclear reactions from chapter 28, etc. Nature tends towards stability, which means that we like exothermic. We like to release energy. So when you get a nucleus that is high energy, highly unstable, then radiation is one of the ways that that nucleus can stabilize. We can spit out particles, we can radiate energy, or both, in order to stabilize the nucleus. So what type of nuclei create radiation? Heavy nuclei. What we mean by heavy, it's got a lot of protons and a lot of neutrons. So the question becomes, well, why are those nuclei radioactive and the lighter ones are not? I'm glad you asked. Well, the issue with the nucleus is that there's actually two of the major forces going on inside the nucleus. One is electrostatic repulsion. Protons repel protons. And the other, acting at the same time, is the strong nuclear force. Now, the strong nuclear force is called the binding force. I can't really give you an analogy here because there's only one place in the universe where the strong nuclear force exists, and that's in the nucleus. So, with electromagnetic, a lot of times we use the analogy of a magnet. If you take the north end of a magnet and attract it to the south end of a magnet, you can feel the attractive force between them. But there's really nothing that we can compare to when we're talking about the nuclear force. So do note there are two forces. One that's kind of pulling the nucleus apart, proton-proton repulsion. And the other one is the binding force, the strong nuclear force that's holding all of that together. So this is definitely a slide you want to pause and put into your notes, but I'll answer that question. What is the purpose of the neutrons? Well, the purpose of the neutrons is to affect d squared. Neutrons create distance between protons. So they reduce the electromagnetic repulsion between those protons. Remember, if we're talking about the nucleus, Q1 and Q2 are both positively charged, and we know that they repel each other, so they're pushing apart. Well, the neutrons get in there as sort of a buffer between them. So then the question becomes, well, why not just dump a whole bunch of neutrons in there? Well, the issue is that the neutrons are very heavy particles, and the strong binding force can't hold that together. So literally, the nucleus gets too heavy and falls apart. But at least for the smaller atoms, the protons do a really nice job of creating distance between the protons. Okay, here's another definition you might want to put into your notes. The strong nuclear force. Protons attract protons. Wait a minute, Miss Burnett, you just said protons repel protons. They do. They also attract each other. They repel each other through electromagnetic repulsion, but they also attract each other through the strong nuclear force. How? Don't know. Neutrons attract neutrons, and protons attract neutrons. So there is an attractive force holding them all together, and that's called the binding force, or the strong nuclear force. All right, so what happens then when our nucleus gets too heavy and starts to radiate particles in energy? Well, there's a lot of different types of radiation. We're only going to talk about four major ones here. The first one is called an alpha particle. Now, when they're talking about alpha particles and they're writing it in the regular text, they're going to use the Greek symbol alpha. But if it's in an equation, they're going to write the isotope notation for helium. And in a nuclear equation, we're not using the electrons. So they don't include the charge. But if this is a helium nucleus, that means that we have no electrons, and it really has a positive 2 charge. They just don't write the positive 2 charge in with the symbol. So when we write an alpha notation symbol in a balanced equation, we're just going to write the isotope notation for helium. Now, these are very low energy particles, but they're very large, and they tend to do damage when they infiltrate things like our food supply. But usually they're not damaging at all because they're easily blocked. Like this says, it can be blocked by a sheet of paper. All right, so what do they want you to know on the test? For each of the radiation parts, they want you to be able to write the isotope notation. They want you to describe the particle, and then they want to talk about, well, how penetrating is it? In other words, how dangerous is it if it can penetrate your body and cause damage to you? And why is it penetrating or not penetrating? So we're going to go through that in a chart. But I'm just going to give you the basic definitions first. All right, beta particles. A beta particle happens when a neutron spontaneously turns into a proton and an electron. And where is the one place in the universe an electron cannot exist? It's in the nucleus. So it gets spit out of the nucleus at a high speed. So now we have a high speed particle, which kind of makes it dangerous. But what do we know about the mass of a proton? It's very light. So in order to be particularly dangerous form of radiation, you have to have mass, you have to have velocity, but you also have to have the ability to not be slowed down by charges. So an electron will, a beta particle has a negative charge, so it will be attracted to the positive charges and the materials that it tries to penetrate, and that will slow it down and it will lose momentum. So these will penetrate wood to an extent, but they're blocked by metals. So how do we write it? Again, in the textbook literature, if we're writing about it just in terms of normal paragraph, we'll write the Greek symbol beta. But in a nuclear equation, we're going to write E for electron. We're going to write 0 for the mass number. Now, it's not 0, but it's close to 0, so we're going to round it down. Pardon me. And we're going to put a -1 for number of protons. And the reason why is because we're taking a neutron and we're turning it into a proton, and that's going to change the balance of the number of protons. So we have to account for that. So the -1 doesn't represent the charge on an electron. It represents the fact that we are creating protons. All right, so we say that the beta particle is not very massive, so it's not going to be very dangerous. It is high in energy, though, so it will penetrate wood, but it is blocked by metal. Also, the negative charge on the electron slows the particle down. Gamma radiation, the thing that made the Hulk. Well, in real life, all gamma radiation does is give you leukemia, cancer. So that would not have been a very interesting story. So I understand, the Incredible Hulk, gamma rays and became the Hulk. So try not to expose yourself to gamma radiation. Most of the gamma radiation we get comes from outer space and is filtered through the ozone layer. All right, high energy rays, which means that it is not a particle, it's just energy. Sorry, I'm left-handed and I keep hitting the slide. So when we write the Greek symbol gamma, if it winds up in a nuclear equation, we just write gamma again because it's not a particle. Now, although it's not a particle, it will penetrate things because of its high energy, and it has no charges to slow it down. So this thing will penetrate metal, except for lead. So a little lower in energy, we have our X-rays. And again, high energy wave. They're not as high as gamma rays, but when you go to get X-rays, a lot of times what they'll do is they'll put a plate of lead over your vital organs so that you're not getting exposed to the X-rays. And then this one is found in chapter 28 only. It's something called a neutron emission, and this is going to be one of the most dangerous forms of radiation. We'll write an N if we're talking about it in regular literature, but if we're writing it into an equation, we're going to write N for neutron. Neutron has a mass of 1, and it has no protons. Now, these are particularly dangerous because they have both high energy and mass, and does a neutron have any charges to slow it down? The answer is, of course, no. It's neutral. So these are the type of particles that would be used, for instance, to start a chain reaction in a nuclear explosion. All right, so explaining the penetrating ability comes down to two things. One, kinetic energy, 1/2 mv squared. You got to have mass, you got to have velocity in order to be dangerous. Also, Coulombic attraction causes the particles to lose that kinetic energy. So if it has a charge, like an alpha particle or a beta particle, it loses energy when it goes to penetrate an object. All right, so let's do a quick summation here. Alpha particle notation, we said, okay, we're going to write helium with 4 neutrons, 2 protons. For a beta particle, we're going to write E for electron, no mass, -1 because we're converting a proton into a neutron. Gamma, we just write the Greek symbol gamma because it's energy, not mass. And to be a isotope notation, you have to be a particle. And neutron, again, N for neutron, 1 for the mass, 0 for the protons, and yes, you have to memorize these to write nuclear equations. Description of an alpha particle, it is a helium nucleus. A beta particle, a neutron turns into a proton plus an electron, and then the electron leaves the nucleus at high energy. So I'm not going to do the whole chart here. You can go back and do the descriptions for gamma and neutrons. That's generally what I do, so I would advise stopping the video and taking that for your notes. Penetrating ability for alpha, blocked by paper. And what explains the kinetic energy of the alpha particle, why it's not very penetrating, is it has mass, but low velocity, and the 2+ charge slows it down. So at this time, you're going to go back and go through the notes and fill out the rest of the chart, because that's what I would have you do in a regular class. Okay, balancing nuclear equations. Actually, balancing nuclear equations is a little easier than balancing regular equations. We're going to use this as an example, but I'm going to give you some background information first. Let's copy this and let's paste it, because you know I like that. Paste the image. Okay, before we get to that, you have to understand there are two types of nuclear equations. Again, our nuclear reactions. This is chapter 28. And we're going to write nuclear reactions. There's something called fission. And fission behaves a lot like a decomposition reaction. In fact, they'll sometimes use the word decay in the problem. And in fission, what you're doing is you're taking a large nucleus and you're breaking it down into smaller particles. And we're going to use an example of that for balancing nuclear equations in just a moment. For fusion reactions, these are like synthesis. And they tend to be, although not always, they tend to be small nuclei. And we are going to combine them. So let's just write small nucleus plus small nucleus. And we're going to combine them into a larger atom. So what do they like to do on a test? Well, they'll do something like this. They'll say, all right, suppose we have hydrogen 1 and we're going to combine it with tritium. And they'll say, well, what is the resulting particle? Well, this is pretty easy. All we have to do is add the two mass numbers together, the 1 and the 3, to get a mass of 4. And then we add the protons together to get a mass of 2. And then we have to look up the particle. So we go to the periodic table. Which particle has 2 protons? Glad you asked. It is a helium particle. So again, notice I'm not writing the electrons because electrons are not involved in nuclear reactions. So again, you are going to add the mass and then add the protons. Now they might get tricky with you and try to do something like this. Right, so suppose they give you this, and they say, all right, we're going to take an oxygen 16 atom, and we are going to fuse it with a particle, and we're going to get all of this mess out of it. We're going to get, actually, I guess that's not really a fair example, because that's not really possible, but we're going to stick with it anyway, forgive me. Suppose we get all this mess. What is the particle X that you have to add to oxygen? All right, again, not hard. We have a total of, oh boy, I screwed this problem up big time. Sorry. Let's change this a little bit. I hate when teachers do this too. Let's make this, try to get too clever. Let's make this sodium. Sorry about that. So we know we have a mass of 16 here on the left, and we have a total mass of 26 on the right. So that means that our particle X has to have a mass of 10. We have a total of 11 plus 2 minus 1, so 12 protons. And we already have 8 protons here on the right, so our particle has to have 4 protons and a mass of 10. And then we look up that particle on the periodic table, and it's beryllium. Now, they could ask you for the isotope notation as the answer, or they could ask you to write nuclide notation. So we'd write this as beryllium-10. All right, so now that I messed up that example, let's give you a easier example to do. I said, all right, we are going to create a magnesium isotope, and we're going to start with carbon 12. What particle X do you have to fuse with carbon 12 to get magnesium 25? So go ahead and pause this, work it out, come back. I'll wait for you. Hey, I waited. All right, so both sides have to have a mass of 25. So particle X has to have a mass of 13. Both sides have to have a total of 12 protons. So that means particle X has to have 6. And then when we look up particle X, we get carbon. So we would say that we have to add carbon 13 isotope to carbon 12 to fuse them together to get magnesium 25. Okay, so let's go back to our fission reaction, because this one's a little more difficult. So they give you a problem like this, and they say, hey, uranium-238 undergoes the following radioactive decays. 2 alpha decays, then a beta decay. What is the resulting isotope? All right, so here's how you do this. You know you're starting with uranium-238. Okay, well, I would look up uranium and find that I have 92 protons. Next, we're going to break this up into 2 alpha decays. Now, you could put a coefficient in front of the alpha particle, or some people like to write the alpha particle twice. And then it's going to undergo a beta decay, so we write a beta particle. And then we know our last particle here is X, so let's solve for X. Both sides have to have 238 for their mass, so X has to be 230. Both sides have to have 92 particles, so we're going to have X plus 2 minus 1, so our particle has to have 89 protons. Again, this will be 89, oops, should put it over here. This will be 89, and then we're going to add it to 4 for 93, and then we're going to subtract 1 for the beta particle to get 92. So 89 is the correct answer. And then we look up 89 on the periodic table, and we get some stuff, some things. Actinium. So in other words, the particle left over is actinium-230. Right. Really very easy. Easier, I think, than balancing regular equations. Alright, so let's see if I covered everything that I wanted to in this slideshow. Oh, let's do average mass. I know that some of you went over this on Friday if it's the summer course, because I'm a little bit behind here in my videos, but let's take a look at what they mean by average atomic mass. So we said that there were 3 isotopes of hydrogen: protium, deuterium, tritium, with masses of 1, 2, and 3. And if we take their abundances and average them, we get 1.008, which is the value that they put on the periodic table. So the table is showing you the average particle. Okay, great. So they give you a question like this. Now, just like with almost anything else in mathematics, if it's commutative A times B, then doing it B times A is going to give you the same answer. So I know some people teach this a little differently. I'm going to show you what I do, and then you are welcome to do it either the textbook way or your recitation teacher way or my way, as long as you get the right answer. Okay, so here's the formula. If we want to do average mass then what we're going to do is we are going to take the abundance of isotope 1, so let's call this abundance 1, and we're going to multiply it by the mass of isotope 1, and we're going to add that to the abundance. Here there's only 2 isotopes, but this could keep going. Abundance for isotope 2 times the mass of isotope 2 plus ... the abundance of however many isotopes you have. Abundance for isotope, let's call it N, times the mass of N. So when you write the formula on an FRQ, you only write it for the number of particles that you have, and in this case I only have 2 isotopes, so this is my formula right here. Alright, so now I'm going to substitute in. I'm going to write average mass equals the abundance of particle 1. Alright, so in your textbook they have you do 98.50 and then multiply it by the mass of a carbon-12 atom. I'm just going to convert it to decimals right here, and I'm not even going to document it. This is one of the few times where I would allow students to not document it. So I'm going to write 0.985 rather than dividing everything by 100 at the end. But whatever works for you is fine with me. Now this carbon-12 thing, if they don't tell you what the actual mass of carbon-12 is, because again, in the formation of a carbon-12 atom, you would lose some of that mass to energy. That was the whole E equals mc squared thing from Einstein. Then if they don't give you a mass, assume the mass to be 12. But in this case, they did give us a mass, so I'm going to use it. 11.998 AMU. And I'm going to add it to the abundance of the other isotope, which is 0.01500 times 13.987. Now do understand, when we put this on a test, we're not going to give you the same abundances as would be found naturally, because then you would just have to look up the mass on the periodic table and get the right answer. So we're going to kind of mess with these mass numbers and abundances. We're going to say, hey, a particular sample has these abundances, and then you would have to calculate the average mass of the sample. In this case, what's the average mass of carbon? So we expect it to be around 12.011. So let's work this out. So 0.9850 times 11.998, and I get 4 sig figs, so 11.82 AMU. So notice we're going to add this together now. So we're going to the hundredths column there. Second isotope, 0.015 times 13.987, and I get 0.2, and we got 4 sig figs here, 098 AMU. So the rule for adding sig figs with addition is you add them up normally, so I'm going to do that. Add 11.82 to that, and I get 12.0298, and then we're only going to go to the hundredths column, so we get 12.03. Now in this case it came out to be 4 sig figs either way, so we got lucky, but it may not always. Alright, so there's a couple of these to try. Practice problems, practice tests, worksheets, etc. But that's the format for all of them. There's nothing different about it. We're not going to ask you to give you an average and then ask you to come up with the parametrics for the abundances. That's an AP level question. We're just going to stop it here.